Today we're going to go over some related rates problems that have trigonometry in them. It's all right triangle trig that we're going to be doing with these problems, which means SOHCAHTOA. When we do related rates problems, or whenever we do any kind of trig in calculus, the angles have to be in radians, or else the calculus, the taking derivatives, will not work correctly. So if you're given a problem that has degrees for their angle measurements, you can just convert the degrees into radians by multiplying by pi over 180. That's just something that you probably remember from Algebra 2. So this is a little formula that you'll need every once in a while. Like in this next example, they're talking about a hot air balloon. So I'll give you a couple minutes. You might just want to shut off the video to copy this problem down. But there's a hot air balloon rising from the ground. It's being tracked by a rangefinder that is 500 feet from the liftoff point of that balloon. When the angle of elevation is 45 degrees, the angle of elevation from the rangefinder, this angle increases at a rate of 8 degrees per minute. And what we're going to try to find is how fast the balloon is rising at that instant, or at the instant where the angle of elevation is 45 degrees. So what we have to do is figure out how to draw the diagram of this, how to label it with the variables, and then try to get an equation that relates those variables. So I'll go over to the next page and we'll draw this picture here of the hot air balloon. Let's see. So here's a hot air balloon, and it's rising, so it's going straight up from the ground. And there's a rangefinder that's 500 feet away. So I'll put the rangefinder here. Here's just a little box for the rangefinder. Now there's an angle of elevation up to the balloon from the rangefinder. So we'll just make that a theta. And remember, with related rates problems, we have to take the derivative before we plug in the angle measurement that they gave us and the 500 feet. Well, the 500 feet is actually a constant in this. This rangefinder is not moving. So we can mark this already as 500 feet. Constant. This balloon is rising, so we can call it anything we want. I guess we can call it h for the height of the balloon. And now you can see that we have two variables, theta and h, and we can actually set up some trigonometry, just SOHCAHTOA, knowing that the tangent of theta is equal to h over 500. So let's put down some of the things that we know already. We know that we're given in the problem that d theta dt, which is the change in that angle per time, they told us it was 8 degrees per minute, but we're going to have to multiply that by pi over 180 to get it into radians per minute. So when you reduce 8 over 180, it reduces down to 2 over 45, so we'll get 2 pi over 45, and that's radians per minute. This angle we'll plug in a couple minutes after we take the derivative, after we get the equation written down. We'll plug in 45 degrees, but we're going to have to turn 45 degrees also into radians. So how do we relate these two variables, the theta and the h? Well, like I just said, SOHCAHTOA says that the tangent of theta is equal to opposite over adjacent. And this is in terms of feet. So now what we can do is we can take the derivative of this with respect to time. So the derivative of tangent is secant squared. So we have secant squared of theta, d theta dt, is equal to, well, this is the same thing as 1 over 500h. So 1 over 500h, the derivative of that is just 1 over 500, because that's a constant, and then we have dh dt. Now this question asks, how fast is that balloon rising? So we want to know the change in the height. We want dh dt. So we'll mark that down here. We want dh dt. So now we've taken the derivative, and now's the time we can plug in the information that's given to us. Theta is equal to 45 degrees, and we're taking the secant squared of that. Well, the secant squared of 45 degrees, well, 45 degrees is pi over 4. I think I'll put the squared on the outside because we're actually going to take the secant of pi over 4 and square that. D theta dt we found up here, so we can just replace that with 2 pi over 45 is equal to 1 over 500, and what we want is dh dt. So really all we have to do is multiply both of these sides by 500 and we'll get the answer to this problem. Well, the secant of 45 degrees, or pi over 4, hopefully you remember from your 45, 45, 90 triangle that secant is hypotenuse over adjacent, and the hypotenuse of a 45 degree triangle is the square root of 2 over 1. So we're actually going to square the square root of 2 because that's the secant of pi over 4. We'll multiply that by 2 pi over 45. And then if we multiply both sides by 500, we're going to get what we need is dh dt. And if we do our math here, 500 times 2 is 1,000, times 2 is 2,000 over 45, 2,000 pi over 45. And I think I'll just math frac 2,000 over 45, see what that reduces down to. That reduces down to 400 over 9 pi. 400 pi over 9. And dh dt, the change in height is feet per minute. So there's the answer to that problem. So there's a little trigonometry for you. Let's do another example. Here's a second example. There's an 80-foot building that makes a 60-foot shadow on the ground at some moment in time. And at this particular time, the angle that the sun makes with the ground is increasing at a rate of 0.27 degrees per minute. The question is, at what rate is the shadow decreasing? So you usually have to read these a few times to figure out what the picture might look like. And in this example, here's an 80-foot building. We know that does not change, so we can label this as 80 feet. Now what's happening is that there's a 60-foot shadow that's being cast on the ground, and remember that shadows decrease or increase over time. So here's the shadow. I'm not going to put 60 here right now because this is a variable. I guess I'll just call this S for shadow, even though I don't like to use the letter S because they look like 5s. But here's S for shadow. And the sun is coming down somewhere and creating this shadow on the ground. And we have an angle that the sun makes with the ground, and we'll just call that theta. And what they tell us is that the angle is increasing at a rate of 0.27 degrees per minute. So that'll be d theta dt. But what we want to do right now is we want to set up a relationship between our two variables, theta and s. And just like in the previous question, we have a tangent situation because this is a right triangle. So we can say that the tangent of theta is equal to 80 over s. And what do they want in this question? They want to know the rate that this shadow is decreasing. Oh, so this shadow is getting smaller and smaller. So they want ds dt. So ds dt is who knows what. And now we can take the derivative of this with respect to time, and after that we'll plug in the two pieces of information that is given to us, the 60 feet shadow and the 0.7 d theta dt. So the derivative of the tangent is secant squared. So we have secant squared of theta, d theta dt, is equal to, well, this 80 over s is the same thing as 80 s to the negative 1 power. So the derivative of that is equal to negative 80 s to the negative 2, which is negative 80 over s squared, ds dt. After we take our derivative, then we can plug in the information that we need. Well, the secant squared of theta, we don't know what theta is at this moment, but we could figure it out because now after we've taken the derivative, we can call s 60, and the secant is the hypotenuse over adjacent, the secant of this angle. We don't know the hypotenuse, but we can see that 60 squared plus 80 squared by Pythagorean theorem is equal to c squared. And if we do the Pythagorean theorem, 60 squared plus 80 squared equals, I guess I'll call that c squared. If we do our math, we can see that c is equal to 100. So the secant of this angle is hypotenuse over adjacent, and we're going to square that. Well, 100 over 60 turns into 10 over 6, turns into 5 over 3. So the secant of theta is 5/3. We're going to square that. Now d theta dt was given to us, but it was given to us in degrees, so we're going to have to take that off to the side and figure that out in radians. d theta dt is 0.27, and now we're going to have to multiply that by pi over 180. And if you take your calculator out and do 0.27 over 180, oops, let me see that, 0.27 over 180, and I'll math frac that, and it becomes 3 over 2,000. So d theta dt is actually 3 pi over 2,000. So we'll plug that in for d theta dt. 3 pi over 2,000 is equal to negative 80 over, now we can plug in s is equal to 60, so we have 60 squared, and what we're asked for is ds dt. So we'll just put in ds dt. And so now all we have to do is a little bit of math here. 5 over 3 squared is 25 over 9 times 3 pi over 2,000. And now we can just multiply both sides by 60 squared over negative 80. So times 60 squared over negative 80, and that should be equal to ds dt. So I think it's just time to take our calculator out and do some calculations here. So without the pi in there, I'll do 25 times 60 squared. See if you can see my calculator here. Times 3, also in the numerator. And in the denominator, we have 9 times 2,000 times negative 8. And then there will be a pi on the top of that. And let's see, I must have made a mistake here. Let's see what's going on. Well, I found out my mistake, and it was because I put an 8 in the denominator instead of an 80. So when you do your arithmetic in your calculator, that's probably the fastest way. You get negative 3 over 16. So we're going to attach a pi to that. So this rate of change is equal to negative 3 pi over 16, and that will be in feet per minute. So that's the answer to our problem. That's the rate of change in the shadow, that it's decreasing. So the only thing now I want you to do is take your textbook and practice a couple problems on page 148. These are baseball diamond problems. They have nothing to do with trig. The trig questions we'll practice tomorrow in class. These are just the old ones, similar to what we were doing earlier this week. Excuse me. Have a great day. Have a great night. Great day. See you tomorrow.